So the last video for this session is on free falls. Okay, so a free fall is basically when I have something falling, like an object falling, right down, and the only force that's acting on it is gravity. So no other forces. It's important to note here that air resistance is either going to be ignored or is negligible. And we'll talk about air resistance later. So the only force acting on this object that is falling is gravity. And you should know that gravity accelerates acceleration due to gravity is 9.8 meters per second squared. But sometimes we'll just use 10 meters per second squared for simplicity. But the value is really closer to 9.8. So what that means is that gravity accelerates all objects, regardless of weight, mass, surface area, any of that, at a rate of 9.8 meters per second squared. So this is an interesting concept because that would mean that any two objects thrown from the same height with the same initial speed or the same initial velocity would accelerate at the same rate and hit the ground at the same time. We know that that doesn't actually happen. For example, if I drop a coffee filter, which is kind of like light and airy, looks something like that, right? It's not the best drawing. Versus like a rock, the rock will probably hit the ground first, and that's actually because of air resistance. And we'll talk about that in more detail later. But basically, air resistance kind of counteracts gravity. It pushes the object up. And air resistance has a bigger effect on something like a coffee filter, which is light and has a lot of surface area, versus a very dense rock. Okay, so let's look at an example of a free fall problem. Okay, so let's say I'm standing on a building that's 120 meters tall. Let's say that I throw a rock off the building, so it goes right down. And let's say that I just kind of drop it. I don't really force it down, I just drop it. So that what I'm trying to say is that initial velocity in this case will be 0. I just kind of drop the rock. Now, neglecting air resistance, the only force acting on this rock is gravity, so G, which accelerates everything at a rate of 10 meters per second squared. I'm going to use the 10 instead of the 9.8 for simplicity. Now, how long would it take the ball, or the rock rather, to fall to the ground? Okay, so remember from the last video, we have 3 important formulas. We know that VF equals VO plus AT. We also know that delta X equals VO plus 1/2 AT squared. And then we also know that VF squared equals VO squared. And I'm using VO instead of VI, but they're interchangeable. It just means initial velocity. So let me actually change this one to an O. Plus 2A delta X. Okay, so we know, let's make a list of the things that we do know. So we know VO time delta X and then acceleration. So we know that VO is 0. We don't know final velocity. We don't know time. That's what I'm actually asking you for, right? We know that change in position is 120 meters because the ball is falling from here to here, so that's 120. And then we know acceleration is 10 meters per second squared. Okay, so and really what I'm asking you for is time. I just like to make this chart so we can kind of get an idea of all the factors that we know or don't know. Okay, so if I'm looking for time, I definitely don't want to use this formula. I have enough to use this guy here, the second one. I don't have enough to use the first one, because I don't know VF, and I also don't know time. And I just need one unknown in this case. Okay, so what I can do is plug right into the second formula and solve for time. Now I just want to make a note on direction. So, because these are vector quantities, acceleration, velocity, and delta x are vectors, it's important to define what is a positive direction and what is a negative direction. So in this case, I'm kind of saying that gravity, which moves downwards, I'm calling down the positive direction. Also, I'm throwing the ball down, or I'm really just dropping it and it's falling down. So initial velocity is also down, which I'm also calling the positive direction. And change in position is also with respect to the downwards direction. Like, I'm going down from here to here. Okay, so that is also in the positive direction. So they all agree in direction, so they can all just be positive. In the next example, we'll see where they don't agree. So I plug in, and I get that. So I know delta x is 120 meters, and VO is 0. There's 1/2. Acceleration is 10, and then we're solving for t. Okay, I'm actually going to bring that to the next page so I have a little bit more room. So 120 meters equals 0 plus 1/2 acceleration, which is 10, sorry. 10 meters over second squared, and then that's t squared times time squared, and I'm solving for time. So I can simplify that down as 120 meters equals 5 times meters over second squared, just multiply the 10 and the 1/2, times t squared. I'm going to divide by 5. My units end up just being seconds squared. So 120 divided by 5, that is 24 seconds squared equals t squared. Square root both sides. So square root 24, I can rewrite that as 2 root 6 seconds equals time. So that's my answer. And, you know, when you take the square root of something, you usually have two answers, plus or minus, but I can't have negative time, so it's just the positive answer, plus root 24, which simplifies to positive 2 root 6. Okay, let's go into a more complicated example. Okay, on the next page, let's say that I am standing at the top of a 20-meter cliff. So I'm right here. And let's say that I throw a ball upwards. So I'm throwing it up. And let's say that I throw it up and its velocity, its initial velocity, is 30 meters per second. Okay, so this is in the upwards direction. Remember that acceleration due to gravity is 10 meters per second squared, and that's always in the downwards direction. Remember that acceleration and velocity are vectors, so now the vectors are in opposite directions. In the last example, they were in the same direction. They were both moving down. I threw the ball down. In this case, I'm throwing the ball up, so acceleration is working in the opposite direction as velocity, so it's pushing the ball back down. So, remember that acceleration is the rate of change of velocity. So after 1 second, say this is 1 second and the ball is here, my new velocity is 20 meters per second. The ball is slowing down because the vectors are in opposite directions. After another second, so at time 2 seconds, the ball is here, and my new velocity is 10 meters per second. So for every second, it's slowing down by 10 meters per second. Now let's say at 3 seconds, the ball would be right here, so this is 3 seconds, and its velocity is 0 meters per second. So what ends up happening when the velocity of the ball is 0 meters per second is that it changes direction, and now it starts to fall down. So now it's going, I'm going to put it in red, in this direction. Now, after another second, the ball is here, so this is a total of 4 seconds. And the velocity of the ball is 10 meters per second, but in the downwards direction. So I'm going to call that negative 10 meters per second. So I'm defining the downwards direction as negative and the upwards direction as positive. Now, let's say at time 5 seconds, so it's 2 seconds after it's changed direction, the velocity is negative 20 meters per second. After another second, the ball is right here, so that's after 6 seconds, and the velocity is negative 30 meters per second. So notice that the ball is actually at the same exact height it started at, so this is the same height, and the velocities have the same magnitude but opposite directions. So when I throw a ball up in the air, the amount of time it takes for the ball to travel up and then to travel back down are equal. So that kind of cuts this whole thing in half. You think about it like that. Okay, so it took 3 seconds for the ball to go up to reach its maximum height, and then 3 seconds for it to reach its initial height. Okay, but let's remember that now the ball is actually going to fall off the cliff. It's going to go all the way down to the ground. So that's going to take another 1 second, and the velocity will be 40 meters per second in the negative direction. Okay, that's at 7 seconds. So we need to figure out how much time is it going to take for it to reach the ground. And remember that the cliff is 20 meters above the ground. Okay, so there are 2 ways we can do this kind of problem. So the first way is we already know the time that it takes for the ball to go up. So this portion right here is 3 seconds. And the time it takes for it to go back down is another 3 seconds. So all I need to do is figure out the time it takes to reach the ground, okay, and then add them all up. So that's the long way. We'll do that way first. So now all I need to figure out is how long does it take the ball to go from here to here, given that its initial velocity, or its velocity at that point, is negative 30 meters per second. Gravity, or acceleration, is negative 10 meters per second squared, and it's got to travel a distance of 20 meters. So again, I can use the same formula that we used in the last problem. And I get that, I'll put it on the next page. So we know that delta x equals VO times time plus 1/2 acceleration t squared. Okay, so we're looking for it to drop another 20 meters. So I'll make the chart. So what's VO? What's V final? What's acceleration? What's time? What's change in position? Okay, so we defined the downwards position as negative. So we're saying that acceleration is negative. Okay, so that's negative 10. The initial velocity, because we're really just looking at from this point right here, down. So we're basically ignoring all of this. So we're just looking at right here. That velocity is negative 30 meters per second. Okay. We don't know final velocity. We don't really need it. We're looking for time. Okay. And then our change in position is from here to here. So we're looking for it to fall from the top of the cliff to the bottom. And since this is a downwards direction, we're looking for it to fall negative 20 meters. So change in position is negative 20. Now I can plug in and I get negative 20 equals VO, which is negative 30, times time, which we don't know, plus 1/2 acceleration, which is negative 10 t squared. So negative 20 equals negative 30 t minus 5t squared. Going to divide everything by negative 5, so I get 4 equals 6t plus t squared. Set it equal to 0, so I get t squared plus 6t minus 4 equals 0. I can factor that. Actually, no, I can't factor that, so I'll have to use quadratic formula. So t equals, and then quadratic formula, negative b, so negative 6 plus or minus b squared minus 4a, which is 1, times c, which is negative 4, all over 2a, and then a is 1. Okay, so that simplifies down to, let's see, so 36 plus 16, okay, so negative 6 plus or minus, let's see, square root 52 all over 2. And then I can take out a 4. Okay, so I get negative 6 plus or minus 2 root 13 over 2. I'll put this on the next page. So negative 6 plus or minus 2 root 13 over 2. And that gets me negative 3 plus or minus root 13. And that ends up being about 0.6 seconds. There's a negative solution to that as well, but remember we can't have negative time. So that means that it takes 0.6 seconds for it to go from here to here. So the total time the ball is in the air is the 3 seconds it was up here, the 3 seconds it was here, and then the additional 0.6 it was here. So total time, t, total time is 3 seconds plus another 3 seconds plus 0.6. Okay, so total air time is 6.6 seconds. So that's the long way of doing this kind of problem. And then there's a short way. So let's go back to the original diagram. Okay, so we see that initial velocity for the whole process, okay, is here, is right, this velocity, 30 meters per second, okay. Acceleration is constant throughout. It's negative 10 meters per second, and that's due to gravity. All right. And then displacement for this whole process is negative 20, right? Because it's going, if we're defining the downward direction as being negative, it's starting at positive 20 and going down to 0. So displacement is negative 20. So we can kind of set up another one of those charts for the entire process, going from here to here. Okay, so really, if you notice, if we just take into consideration the entire process, this is my final position, or this is my initial position, sorry, and this is my final position. And if my final position is 0, and this is 20, final minus initial gets me negative 20. Okay, so let's set up another graph, or table. This is the second way to do it. So again, we have to identify everything that we know. We know VI, so now we're saying that VI is 30 in the positive direction because I'm considering when the person threw the ball upwards. We don't know VF and we don't really need it. Okay, we're looking for time. Acceleration is constant, it's negative 10. And then change in position is negative 20. So plugging into the same formula, delta x equals VI times time plus 1/2 acceleration times time squared. So negative 20 equals 30t plus 1/2 negative 10t squared. Can simplify that. So negative 20 equals 30t minus 5t squared. Divide across by negative 5, so 4 equals negative 6t plus 5t squared. Set it equal to 0. Oops. That should have been 1t. Okay, so set it equal to 0, and I get t squared minus 6t minus 4. Again, I can't factor it, so I have to use quadratic formula. Okay, so t equals negative b, so negative 6 times negative 1 is 6, plus or minus square root of b squared, which is 36, minus 4a, which is 1, times c, which is negative 4, all over 2a. That simplifies down to 6 plus or minus the square root of 52 all over 2. Okay, and that gives us 6 plus or minus 2 root 13 all over 2, which gives us 3 plus or minus root 13, and that's about 6.6 seconds. Again, there will be a negative answer, but you can't have negative time, so we just ignore that answer. Okay, so we see that we get the same answer doing it this way, but in fewer steps. So that's just another way to solve a free fall problem. And that's about it for free falls. So in the next couple of videos, we'll consider projections and vector components.